Assalamualaikum warahmatullahi wabarakatuh and good morning to everyone. So today we're going to continue our lecture number 7. The topic for this lecture is device management via operating system. So a device manager manages every peripheral device in the system. If you in the Windows, you can right click your My Computer and you can see the list of devices that installed in your machine. Okay, so the device manager also maintain a balance between a finite supply of devices with the user's indefinite demand for them. Okay, so any you can install basically a lot of devices that you can install in your machine. Okay, so the operating system manage this. Maybe you want to use same device, or some device are used heavily, some device are lightly used. So what will OS do is to manage your devices. Okay, so this why it maintain the system balance of your machine. All right. So it involves a four basic functions. So basically operating system, in order to manage the devices, basically involve four basic functions. The first one is it tracks the status of each device, whether it's install, uninstall, remove, deallocate, allocate, and also like the driver, whether it's up to date or not. And user preset policies to determine which process get a device and for how long. All right. So maybe you need a device for certain times, like you're running a simulation or something that need longer time rather than you just pick some in. Sometimes you just need a very short functions like calculator or some things that you really don't use it for too long. And also it allocate the device and deallocate device. So allocate the device when you firstly install or you want to use the plug and play device, and deallocate is like you disconnect the device. So there are three categories of devices. The first one is dedicated devices such as printers, tape drive, your hard disk drive, and even plotters, okay, like 3D machine and stuff. So dedicated device assigned to one job at a time. It serves the job the entire time it's active or until it release it. Okay. This one of disadvantage of this dedicated device is allocating a device to a single process is inefficient, especially if not used 100% of the time, meaning the idle and stuff. So dedicated device like printers, you not really like use, but you have to allocate some times or allocate some space for that. The second one is a shared device, like this direct access and a storage device. Okay, it can be assigned to several processes. The device is shared by interleaving their requests. And the third one is the virtual devices. It's a combination of the first two. Dedicated devices are transformed into shared devices. Example is like printer, which is converted into shareable device. You have a network and you are the only machine that connect to the printer, so you just share the printer. Okay, using a spooling program that reroutes print requests to a disk. So you have a printer spooler that manage whether your printer is active or not, or waiting for jobs to be sent, something like that. And then this is the sequential access storage media. Okay, the first generation storage media is what we call a magnetic tapes. So this is the early storage media. It is used for routine achieving and routine archiving and storing backup data. So they have some certain routine you have to follow, and also storing a backup data. Records also are stored serially, and a record may be of any length. It is not fixed. All right. So serially, a serial and parallel. So in serial become it is in a sequential manners. Each record is determined by its position on the tape. So tape is have a position, you have a tracks and stuff. So to access a record, the tape must be mounted and fast forwarded from the beginning until the desired position is located. Alright. It is time consuming. It is up to the minutes. So in this modern world PC, if you try to open certain application, even it takes you 10 seconds or 20 seconds, it is really intolerable in the modern days, in the modern definition of computing. So up to minutes is very very slow. So to imagine this, the size of the magnetic tapes, we assume a reel of tape which is ½ inch wide and 2,400 feet long. Okay, so you have here like this one is the ½ inch, and then this is like really lengthy, 2,400 feet long, 2,400 feet, or equivalent to 28,800. If you do a calculation on inch, is 28,800 inch, something like that. Just Google. And then the number of characters that can be recorded per inch is determined by the tape density. Okay, how many bytes, how many files they can save. So for example, certain magnetic tape has a capacity of 1,600 bytes per inch, or in a standard definition we call it BPI, bytes per inch. Okay, let's say if a record is 160 bytes long and 10 records can be stored on 1-inch tape. You want to see the example? You have a record of 160 bytes long and 10 records can be stored in 1-inch tape. We're gonna see example after this. So this is the sequential access storage media. You have a 3 characters here, 1, 2 and 3. Okay, 3 characters. All this is pretty much we call that in the same this is the column. I can see it's a column, right? So these are characters position like 1, 2 and 3. Okay, data is recorded on 8 of the 9 parallel tracks that run the length of the tape. So there is a parallel tracks. This is one parallel number 1, a parallel tracks number 1 and up until 8, and this is a parallel tracks number 9. So the 9th track holds a parity bit. Okay, that is used for error checking. So whether the file is in error or corrupted or something, so the track number 9 will check it. This is what I call a parity. That the track number 9 holds a parity bit. Okay. The number of characters that can be recorded per inch is determined by the density of the tape. Let's say it's 1,600 bytes per inch. Okay, it is 1,600 BPI. All right. And then so records may be stored individually or in blocks. Individually means that you have this one is record number 1, and then you have some must allocate some space, and this must be record number 2, and so on. This is individually. All right, record 1, record 2 and so on, record 3. All right, record number 3. And then for the blocks is you like record 1, record 2, record 3 in a blocks. This is, let's say, one block, so you have 3 records, and then you have some space for moving the read and write head. Okay, you have like, just imagine this write and read head, which is moving according to the tracks. So magnetic tape move under the read write head when there's a need to access a record. If records are stored individually, each record will need to be separated by space. So this is the space, and this is a space if you record it individually. To indicate a starting and ending. So this is like a starting point, and the head move till this is like the ending point. Okay, starting and ending point. So it starts again, and this is the starting, and this is the end point. So this is how the tape, the read and write head moves in the magnetic tape. If records are stored in blocks, the entire block is preceded by space and followed by a space. So this is the record. If it's in blocks, so record 1, record 2, record 3 will be allocated in blocks until they have a space here. All right, followed by a space. Individual records are stored sequentially within the block. So this is what we call a sequential, or in a serial manner. So a tape moves in jerks. Read, write, a record and stop. Read, write, a record and stop. This is how the tape moves. Okay. Okay, the tape needs time and space to stop, so a gap is inserted between each record. Remember, I show you if like this is a record number 1, and you have some space here, and then this is a record number 2, have some space here, and this is record number 3. Sorry, record number 3, have some space here. And this gap or space, we call it IRG, or inter-record gap, IRG. And it is about 1 inch long, half-inch long. Sorry, half-inch long. Okay, this one is half-inch long. Assuming that a record is 1/10 inch long, so this is like 1/10 inch long, 1/10. And we need to store 10 records, so up until R10, alright? Up until R10, which is still 1/10, 1/10 inch. You need, if you have a 1/10 inch long record, and you have a 1/inch long per record, and you need to store 10 records, meaning that you need a 5.5 inches of tape is required to store 1 inch of data. So let's say you have here R1, 1/10 inch, and you have a space about half an inch, and this is the R2, 1/10 inch, then you have a half-inch space, and this is the R3. R3 you have 1/10 inch up until R10. Okay, this is 1/10 inch. Just don't mind the scale of my drawing. Okay, you have 1 inch, you have a 4 inch of IRG. Okay, 4.5 inch of IRG mean 9 half an inch already, or 4.5 inch. Okay, 9 times half is 4 half, 4.5 inch, and then you plus the 1/10, 1/10 times 10s, 1/10 times 10 records, so you have 1 inch. So 4.5 plus 1 is 5.5. But you see here, the space is wasted just to cover the gap, right? Just to cover the gap. And then you need a 4.5 inch gap to cover only 1 inch of data. So this is really inefficient use of the storage medium. This is what we call the individual, all right? The individual record, okay? So this is, okay, as I said before, you have a record 1 is 1/10 inch, and this is half an inch. Half an inch or 0.5, better is 0.5, or this one 0.1 inch. Okay, so this is 0.1 inch, and this is 0.5 inch, and so on. You have like 9 times 0.5 is like 4.5 inch, and data or record, you have 1/10 times 10, so you have 1 inch. So total you have 5.5 inch. But you can see here, Mostly it's because of the IRG. Your data only take 1 inch, but your IRG takes 4.5 inch. This is really inefficient if you do it individually. Okay. So alternatively, records are grouped into blocks or blocking blocks. Not blocking doesn't mean like it's block or try to withstand whatever. Meaning it's a block. Before recording them to the tape. The number of records in the block is determined by the application set to take advantage of the transfer rate. So the transfer rate is the density times the transport speed. So transport speed usually measured in inches per second or IPS, okay? Inches per second. So density times the transport rate. So if you have a 1600 BPI, or you convert into 1600 bytes per inch, and then you times x inch per second, okay, you have a 1600 times x bytes per inch, okay. So this is how you calculate how many like the capacity you can accommodate based on the bytes BPI and the transport speed or IPS, inches per second. Okay, here you have here IBG. Here is still 0.5 inch, and this one is 1/10. So this one you take about 1 inch, and this one is still a 0.5 inch. Okay, 0.5 inch. All right. So the IBG is still 1/2 inch long. Okay, but it's not stored at 1 inch. So we use a 1.5. So you have 1 plus 1.5. Let's say this will take about 1.5 inch, okay? If you have 10 records, but you store it in a block, in the block manners, so you have 1.5 inch. Previously, individual, we have 5.5 inch. So you see a huge difference, 1.5 and 5.5. So it almost like 3 times. Individually, you need 3 times. In the blocks, you reduce it significantly from 5 to 5 to 1.5 inch, okay. So as you can see before in graphical way, huge space is safe in a block manners. So you can see like two advantage of blocking or block manners. Blocking, I really don't like they use the word blocking, because blocking is like you block, you prevent something to move. Okay. Okay, the first one is fewer input output operations are needed because one read command can move an entire block containing several logical records into main memory. Okay, you only need one read command rather than the previous individual you have 10 read commands. Less tape is wasted because the size of physical record exceeds the size of the physical record or data bigger than the size of the gap. So remember, in the individual you have gap is bigger than the record for individual, but record is bigger than gap for block. Okay, this one is good enough because you need a record or data is bigger than anything else. Space meaning you wasted a space because this is just a small this space is allocated, which is you cannot use for storing a record, storing a data. You just wasted on that just for your arm, your read and write arm to move. But they also have two disadvantage of blocking or block manners. So in order to manage that, if it will incur overhead. So overhead and software routines are needed for blocking, deep blocking, and record keeping. So this is overhead, the management overhead, the control overhead. And then you have buffer space is wasted if you need only one logical record, but must read the entire block to retrieve it. So block comes with this one. If you want to read, maybe you need only a small portion of that whole block. You need you need only one logical record, or there's a specific, a small amount of record, but in order to do that, you have to read the whole block instead of that particular position. So you buffer space, your buffer space is wasted. So you have your benchmark, maximum access, average access, sequential access. So for example, how long does it take to access a block or record on a magnetic tape? So assume that you have a 2400 foot, assume here you have a 2400 feet, or equivalent to 28,800 inch, okay, with a tape transport of 200 IPS inch per second that can be read without stopping in 2.5 minutes, okay. All right, without stopping 2.5 minutes. If you try to this is 1600 bytes. If you calculate the rate of it, bytes per second is like you calculate is like 1000 you calculate like 2400 times 200 is equal to 32, if I'm not mistaken, to 320,000 bytes. All right, okay, you have bytes per second. And then if you want to calculate like how do you get 2.5 minutes, you have this one 28,800 is divided by 200, and you get a 144. Sorry, you have got a 244 minutes. Sorry, 244 seconds. Okay, so 2800 is a inch. Sorry, is an inch, and 200 is an inch per second. So you got a 244 second, which is equivalent to 2.5 minutes. Okay, and average we take half of it, like 1.25 minutes for the average. Okay, so therefore it will take 2.5 minutes to access the last record on the tape. On average, it will take 1.25 minimum to access record. To access one record after another sequentially, it would take as long as it takes to start and stop a tape, like 2 milliseconds. This is the given value. This is the given value, 2 milliseconds. All right. So access time varies widely because magnetic tape is a poor medium for routine secondary storage, except for files with very high sequential activity in a very serial manners, or serial kind of files or execution. But one advantage of magnetic tape is it is a low cost, compact storage capabilities, and good medium for backing up magnetic disks and for long term archive storage. So, if you have a very high sequential activity like 90 to 100%, it's good to use a magnetic tape. Now we go to the direct access storage devices. So a direct access storage device is a device that can directly read-write to a specific place on the disk. Okay, direct access storage devices, specific place on the disk. So also term a random access, classified into 4 categories: a magnetic disk, this is all the storage media; optical disk, flash memory; magneto-optical disk. So we're gonna see these two, magnetic and optical disks, in details. So this is the Fixate magnetic disk storage. You can see this is a pioneer for the hard disk drive. Okay, so you have your, each circle is a track. So this one, track 1 is bigger circle. Track 4, this one going inner. Data is located serially on each track by fixed read write heads. Okay, fixed read write heads. So this is the You have four read-write heads in each track. Let's say this is a four track, so this is the fixed one. It's used when speed is very important. Okay, this is a fixed magnetic disk storage. So the fixed disk is a very fast. Disadvantage is a high cost, reduced storage space compared to the movable hard head disk because the track must be positioned farther apart to accommodate the width of the read and write heads. Okay, so the movable head disk compared reduced storage space compared to movable head disk because the tracks must be positioned farther apart to accommodate the width of the read write heads. Okay, because of that you have an unequal unequal circle between each track, so the track must be positioned farther apart to accommodate the width of the read write heads. Okay, so mobile magnetic hard disk storage has one read write head. So we go into the movable head magnetic disk storage. Before this, a fixed one. It has one read write head rather than if like four, you have four tracks, we must have four read write head. Floats over the surface of each disk. This can be single platter or a part of a disk pack, a stack of magnetic platters. So each platter has two surfaces for recording, the up and the down, the top and the bottom. Each surface is formatted with a specific number of concentric tracks where the data is recorded. So the number of tracks varies, ranges from few hundreds to a few thousands. So this is a cross-sectional of the movable magnetic head. You have a read-write head, up and down here, and you have a platter, and this is a cylinder moving. You're moving the read-write head. So this is a disk pack, several platters stacked onto the common central spindle, separated by some space to allow the read-write heads to move between each pair of disks. Okay, this one read-write head, and then it will move on the different tracks or different sectors or whatever. The arm move to read-write head between each pair of surface. The surface above and below it, the top and the bottom. The arm move all heads in unison, meaning that in unidirectional, one way. If one head is on track 36, then all heads are track on 36. This is filled up track by track. If we fill track 10 of all surfaces, we got a virtual cylinder of data. Okay, if you fill up 10, track number 10 of all surfaces, we can get a virtual cylinder of data. Sorry. To access a record, the system needs to know its cylinder number, so the arm can move to the head of the correct cylinder. Okay, so the arm can move to the head of the correct cylinder. A surface number, so the proper read and write head is activated. Okay, and the record number, so the head knows when it should begin reading or writing. So cylinder for correct head can move to the correct cylinder. Surface of the proper read write head is activated, and a record number, so the head knows when it should begin reading or writing. Optical disk storage. This is like a CD, DVD kind of stuff. Optical storage devices are called disks to differentiate them from magnetic storage disk. So DISCS, optical disk, and magnetic disk. A difference between an optical disc and a magnetic disc is the track and sector design. Two measures of optical disc drive performance. First, a sustained data transfer rate, megabytes per second, and average access time is in a millisecond. So magnetic disc also consists of concentric track of sectors and spin at the counter speed. Because the sector outside of the disc spins faster past the head and inner sectors, outside sectors are much larger than sectors located near the center of the disc. So this format actually wastes in the magnetic disc, usually wastes space but maximize the speed of data. An optical disc consists of one spiraling track of the same size sectors running from the center to the rim of the disc. Center to the rim of the disc. The design allows more sectors and more data to fit on optical disc compared to magnetic disc of the same size. So the disk drive adjusts the speed of the disk spin to compensate for the sector's location on the disk. It spins faster to reach sectors located in the center of the disk, slower to reach sectors near the outer edge. Okay, so if like this is the like this is the center and this one. So it will become faster if it is near the, okay, spin faster to reach sectors located at the center of the, so this is like faster, and along the way out getting outer from the center it become a slower. Okay, spins faster to reach sectors located at the center of the disk, slower to reach sectors near the outer edge. This is the outer edge. This is going towards the outer edge. Sustained data transfer rate is measured in megabytes per second. The speed data is read from the disk. It's for application that require sequential access like audio playback. The average access time is important for application that retrieve data that is not stored sequentially, like random access, like a dictionary. Access time is the average time required to move the head to a specific place on the disk in millisecond. Another important feature of the effects forming is a cache size. A hardware cache acts as a buffer by transferring block of data from the disk. It will anticipate that the user may want to reread some recently retrieved information, so data can be read more quickly if the information is in the cache. It also acts as a read ahead buffer. So read ahead buffer is actually the definition is for, it looks for the next block of info on the disk. So you have a type of optical disk is a CD, CD-ROM. I don't think you use this anyway. But certain, if you buy certain devices, they will give you CD or DVD for the driver. Of course, you can always get a driver from the internet nowadays, or magneto-optical disk. So we go to the direct access storage devices. Access time, we have three factors to determine access time. One is a seek time, search time, which is rotational delay, and a transfer time. Transfer time is like a data time, data transfer. This seek time and search time for the movable, for the read and write head to move around to the correct track, to the destined track and the destined sector. So the seek time is the slowest of three factors. Uh, Seek time is the slowest of the three factors, meaning that is based on the tracks moving in inter tracks. Okay. Search time is for the intersector, and transfer time for data transfer. Okay. So the search time also is known as a rotational delay. It's the time to rotate the DASD until the request record is moved under the read write head. And transfer time is a faster rotary, is the time taken to transfer data from secondary storage to a main memory. So fixed head device access a record based on its tracks number and a record number. The total amount of time required to access data depends on rotational speed. Position of the record relative to the position of where the read. So rotational speed, and of course your position, whether it tracks far away from the your intended tracks or far away from your intended sectors, or either in the same tracks but different sectors. So you can have a total access time is equal to rotational delay plus data transfer time. Okay, this is the access time, rotational delay plus the data transfer time. Rotational speed varies between devices but is constant within each device. So speed is varies between devices, but constant within each device. So you have here, there are three basics operation. Okay, the first one, this is the rotation. A is the best situation. Okay, A is the best situation because the record is next to the read write head. This is a read write head, read and write head. So when again it's moving, so record one is just best because next to the read write head when the input output command is issued. So this one, the rotational delay is considered 0. B is the average situation. Okay, B is the average situation. You can see that the record is directly opposite to the head. Rotational delay actually T over 2. Okay, half of it, where T is the time for one full rotation. So you take half of it. This is the common way. And rotation C is the worst situation. Just record is far away. You have to make one full round before you can meet with the read and write head. Okay. So this the rotational delay is 3 is considered the rotational delay is still considered a T. So this one rotational delay T is 0. This one T is equal T over 2 and this one is T. You have to make one complete round of rotation. So this benchmark maximum access. So how long does it take to access a record? Assume one complete revolution takes about 16.8 millisecond. Okay, one complete revolution. The average rotational delay is 8.4 millisecond. The average is half of it, average access. And the data transfer time varies by 0.0094 millisecond per byte. So this is given. Okay, this is all given. So sequential access depends on the length of the record, generally less than 1 millisecond. This is given as well. You refer to the table in the previous slides. Okay, let's say you have assume record is 100 bytes. Okay, you have 100 bytes long and block contains 10 records. So you have 100 bytes and you have 100 bytes and contains assume a record is 100 bytes. A record is 100 bytes and these blocks contain 10 records in a block manner. If you read 10 records individually, so access time is 8.4 plus 0.094. This is 0.00094 times 100. 0.00094 times 100. Okay, 100 bytes. So the total access time for 10 records is 84 point. This one is 8.494. So total access for 10 records is 84 point. Sorry, it's 84.94 for one record. So the small variance access make DSD suitable for files for low activity application that access records in a random fashion. So record blocking may be done to save some time. All right. This is total access time. 84 is a total access time for one record. If you need if you want like 10 records, you just times 10, so it becomes 84.94 millisecond. All right, 84.94 millisecond. Let's say if we read a block of 10 records, you want to read one block of 10 records, so you have a 8.4 plus 0.094 times 10, so equal to 9.34 seconds for 10 records in one block. So this is 10 records for 1 block, 9.34 seconds. This is the total access time for one record, not one block. And this is the total unit for 10 records of 100 bytes, and this is for 10 record in one block. So just try to differentiate that. So movable head devices, the total amount of time required to access data depends on rotational speed, as I mentioned, position of the record relative to the position in the read and write head. So seek time, total seek time, and also a seek time. So total access time is actually a rotational delay plus data transfer time plus seek time. So this is all the access time. Seek time is the time required to move the arm into position over a proper track. So let's say you have this one is track 1, this one is track 2, track 3. So the arm will, this is the read and write head. So it will move at the track 1, like let's say you want to track 2 and track 3 or something like that, okay? Total access time, the rotational delay plus data transfer time plus seek time. Rotation delay is between sectors in the track, and seek time is inter sector, and data transfer time is for the to transfer to the main memory. So this is the movable head devices maximum access. Let's say you have 50 millisecond plus 16.8 millisecond plus 0.094 millisecond per byte, different from the fixed head. So this is average access, half of it, and the sequential depends on the length of the record, generally less than 1 millisecond. This is a given one, 1 millisecond. Okay. So this is a component of the input-output system. All right. You can see like this dispatcher, this like a call center, and this dispatcher responsible for handling incoming calls as quickly as possible and find out who needs transportation, where they are, and where they're going and when. So each vehicle is assigned like one mechanic. Okay, some mechanic takes more than one vehicles and stuff. All right, so this is specialized mechanic. So this is a component of input output system. If we convert it into the input output system in a computerized way, so this is a CPU just like this dispatcher, and this is channel 1 and channel 2, just like a bus or wired. And this channel 1 control channel 1 manage the control unit 1, control unit 2, channel 2 manage the control unit 3 and control unit 4. So control unit I have this one, this two, this three, tape 1, tape 2, different devices or different disks, something like this. A component of the input output system. So this is just like a dispatcher. Okay. Oh, sorry. This is dispatcher, or no, this is not dispatcher. This is a dispatcher. Dispatcher 1, this dispatcher 2. All right. This is like mechanics, and this is the vehicle. This is the vehicles. All right. So input output channel synchronize the fast speed of the CPU with the slow speed of the input output device. So input channels, the channel synchronize the fast speed of the CPU with the slow speed of him. So CPU have a really high speed, but the input output device has a very slow speed. So it synchronized the input output channels. Overlaps input output operation with processor operation. So overlaps input output operation with processor operation. So the CPU and input output can process concurrently. It's save space, save time, and very efficient. So the input output channel program are used to specify the action to be performed by device and controls the data transmission data between main memory and the control units. So what we have here is the input-output channel programs are used to specify the action to be performed by devices and controls the data between main memory and the control units. You have a main memory and you have the control units. The input-output control unit interprets the signal like rewind for a tape drive and so on. In most systems, one control unit is attached to several similar devices. This in the modern way of the computing. At the start of the input output command, the info passes from the CPU to the channel is read, write, or rewind. A channel number, address of the physical record to be transferred, and starting address of a memory buffer from into which record is to be transferred. So channels are as fast as the CPU and can direct several control units by interleaving commands. Each control unit directs several devices. This is the example diagram. So channel 1 control unit 1, control unit 2. Channel 2 also can control the control unit, can manage the control unit 2 and stuff. And control unit 3 also can manage tape number 2 that also be managed by control unit number 2. The multiple path increase reliability. If you have multiple paths, you increase reliability and redundancy. Okay, let's say one path problem, you still have an like backup path, or this path still working. Okay, if any of the paths malfunction, you still have one option. Okay, each unit in the input output system can finish its operation independent of each other. The system needs to know when a device completes an operation. Of course, you have to inform the system. After device has begin writing a record and before it completed the task, so this one is how you deallocate. The connection between the device and its control unit can be cut off when it almost finished. It's writing a record now before complete the task, you can disconnect, okay? Or you can cut off. So the control unit can initiate another input output task with another device. So you disconnect and the control unit can initiate another input output task with another device. The system needs to know when a device completes an operation. Sorry. Achieve using a hardware flag called channel status word, just to see the status of its devices. It consists of 3 bits in main memory, indicate the status of the channel. So the 3 bits channel, control unit, and device. Each bit change from value from 0 to 1 to represent changes from free to busy. So 0, you have a 0 free, and 1 is busy. So basically indicate the status of the channel. Each component has access to the flag so that the bit can be tested before proceeding with the next input output operations to ensure that the entire path is free and vice versa. Okay. So that you must entire path, meaning the line or the bus must be free. The entire path or the cable or the system bus. 2 ways to perform the test is one by polling. CPU predicate test the channel status bit in CSW. So if the channel is busy, the CPU performs other processing tasks until the test shows that the channel is free. Okay. If the channel is busy, the CPU performs other processing tasks until the test shows that the channel is free. This method of polling is determining how often polling should be done. If like polling is too frequent, the CPU wastes times testing the flag just to find out that the channel is still busy. If too seldom, the channel could sit idle for a long period of times. And the second one is the interrupt. A hardware mechanism does the test as part of every machine instruction executed by the CPU. Okay. If the channel is busy, the flag is set so the execution of the uh, current instruction is automatically interrupted and control is transferred to interrupt handler. The interrupt handler determines the best action to take based on the current situation. Since it's possible for more than one unit to cause the input-output interrupt, the interrupt handler must determine which unit send the signal, analyze the status and restart when appropriate with the next operation, and finally return control to the interrupted process. Okay, you have a polling and you have an interrupt. So now we move to the communication among devices. We have a direct memory access, allows the control unit to directly access a main memory. Once reading writing has begun, the remainder of the data can be transferred to from memory without CPU intervention. So you save time, more efficient and faster reading and writing of the file. Buffers are used to better synchronization the movement of data between the relative slow input device and the fast CPU. So if you try to move from slow input to the faster CPU, you become no, it's not stable. So you have a buffer to accommodate that. So buffers are temporary storage areas residing at three locations: main memory, channels, and control unit. So are used to store data read from an input device before it is needed by the processor and will be returned to the an output device. So it read from the input, write to the output. Read, input, write, output. Double buffering is used to maximize a throughput. So this is the two buffers, okay? Objective to have a record ready to be transferred to from memory at any time to avoid any possible delay. So you have here CPU and disk. Direct transfer is slow because unequal in the processing speed. CPU very fast, input output device is very slow. So while one record is being processed by CPU, another can be written by the channel. Okay, read or written by the channel, something like that. Okay, so this is you have a double buffer. So the device manager handles an input-output request as three tasks, each handled by a specific software components. The first one is input-output traffic controller. It watches the status of all devices, control units, and channels. And you have an input-output scheduler. So it implants a timing, access the device, control unit, and channels. Input-output device handler perform the actual data transfer and process device interrupt. So you have a channel control block here. You have a channel unit control block. And you have a device control block. This you have a channel control block. This one is a unit control channel unit control block. And this one is a device control block. Okay. So the input-output traffic controller to perform a task, the traffic controller maintains a database containing the status connection of each unit in the input-output subsystem group into channel control block, channel unit control block, and device control block. Okay. So the traffic controller also traces backward from the device to the control units to the channels, from the control units to the channel. Okay. If a pass is not available, the process is linked to the queues. kept in the control blocks of the request device, control unit, and channel. And you have the second one is a scheduler. Allocate the devices, control units, and channels. When the number of requests is greater than the available path, it decides which request to satisfy. First, unlike processors, input-output requests cannot be preempted. And you have an input-output device handler, process input-output interrupts, handles error conditions, and provide detail on scheduling algorithm. It is a very device dependent, and each type input has its own device handler algo. So a SIG strategy for the input-output device handler is predetermined policy that the handler used to allocate the access to the device among many processors that are waiting for it. It determines the order in which processors get the device. So your goal, the SIG strategy's goal is to keep the SIG time to minimum. Remember, SIG is between the thread. Common strategies like first come first serve, shortest SIG time first, and scan. So a scheduling algo should minimize a movement, minimize mean response time, and minimize the variance in response time. Okay, we're gonna see the first device handler SIG strategies called first come first serves. Okay, this is just as the name suggests, it's like all the algo before this. It's similar. You first come first serve is the general algorithm that you can use for any system. So the first one is a simple, easy to program, and fair to users. The code, the line code is very simple. Whoever comes first gonna get served. Okay. Example: a single-sided disk with one recordable surface where tracks are numbered from 0 to 49. Okay, from 0 to 49. So you have here again you have here this one is like this is track 0 and this is track 49, or the outer circle, track 49. Assume it takes 1 millisecond to travel from one track to an adjacent track. Okay, one track to an adjacent track. While retrieving data from track 15, requests arrive for tracks 4, 40, 11, 35, 7, and 14. Okay, so this is the diagram of first come first serve algo on the device handler. So the first one 15 to 4, you go for 15 to 4, and then the travel tracks 11 tracks travel between 15 to 4, and then after 4 is come 40, so you like 36 tracks, the 29, 24. So this one 4, and then you travel 36, 40, then you travel 29 tracks to 11, and then you travel 24 tracks to 35, and then you travel 28 tracks to 7, and the last one is 14, 7 to 14. So total number of tracks is 135 milliseconds. This is 135. Take about 135 milliseconds. Average number of tracks travel is 135 divided by 135 divided by how many tracks we have here? 1, 2, 3, 4, 5, 6. So divided by 6, and then you get 22.5, something like that. All right. So we look on the second one, Sstf. We call that Sstf is the shortest seek time first. Okay, shortest seek time first. Okay, the concept is similar to SJN, shortest job. So this one is shorter jobs. The request with the track closest to the one being served is the next to be satisfied. It minimizes overall seek time. Disadvantage is it favors easy to reach requests and postpone traveling to those that are out of the way. Okay, it will take the shortest the shortest location near to the current track. And problem with this, it will ignore or it will come to serve the farthest the farthest or the the most distant tracks later. Okay, it can lead to starvation and stuff if there is keep on the job adjacent or nearby to the tracks requested. So you have here 15. So like start from 15, go to the list. The nearest is 14, and then 14 is 11, and then 7, and then 4. Then you go to the furthest 35, and then 40. Okay, let's say there is a job so requested along this line, along this region. 35 and 40, track 35 and 40 might get stuff, okay, or might not be served at all. So total number of tracks, but it reduce the total number of tracks traveling to 47 millisecond. And 47 divided by 6 is 7.83 millisecond. Average number of tracks traveled. The time taken to specify all requests about 1 over third, okay? 1 over third from the first come, first serve, okay? First come, first serve. Then we have a scan. Scan use a bidirectional beat to indicate whether the arm is moving towards the center of the disc or away from it. It moves the arm from the outer to the inner track, servicing every request in its path. So when it reaches the innermost track, it reverse direction and moves towards the outer tracks, servicing every request in its path. So it move around from the outer to the inner track, from the outer track to the inner track. So servicing every request in its path. So when it reaches the innermost track to the center, it reverses and moves towards the outer track, servicing every request in its path. So this is a directional or one way, a directional. Before this, first come first serve and shortest seek time first, using a bidirectional, depending on depending on the location of the file or the data. But this one we move one way and then serving the other way. So we'll whenever he moves to that whenever the arm head move towards inner or outer track, it will serve all the tracks that request its read or write. Okay, read or write command. So here we go to the inner track first, and then you go to the outer track. Is it inner track from the outer to the inner track? Yes, from the outer to the inner track. Sorry, this is the outer track. Going to the outer track, and then you go into the inner track. This one is close to the center. This one is outwards from the center. So total number of tracks is 61 millisecond, and the average number of tracks travel is 10.16 millisecond. So if you compare the Sstf, a scan eliminates the possibility of indefinite postponement or request in out of the way places, meaning the places farthest away from the current location. As requests arrive, each is inserted in its proper place in the queue and serviced when the arm reaches the track. If track 11 is being served when the request for track 13, 11, if track 11 being served, let's say there is a, okay, track 11 being served, when if track 11 being served while the request for track 13 arrive, let's say this is the current track, and now suddenly there is like track 13, track number 13 request for this arm head and right arm head. The arm continues to track 7, okay, and track 7 and then to track 1. Although it's like nearer to the 11, but but the arm head that currently servicing 11 will go towards the track 7 and 4, and then it will come back to 13. All right. Track 13, this is one of the advantage. Track 13, although it's nearer to the track 11, track 13 has to wait until the arm starts its way back. This eliminates a great deal of arm movement and save time in the end. It can be advantage or it can be disadvantage. All right. But you have to serve 7 and 4 first, and then you come back to 13. So there is also a variations of loop. N step scan, C scan, and C look. Okay. So which strategy is the best? If you think about the simple implementation, less overhead, first come first serve is really suitable for light load. Not mean that the demand is not too high. Service time becomes unacceptably high as the load increase. Okay, you have to you have to must be dynamic to select other algorithm. So shorter seek time first is suitable for moderate loads, localization problem under heavy loads. Okay. First come first serve. That's it. Yeah, as I said before, the track that is farthest away from the current arm and head might not be served at all and might be suffer from starvation. Scan is suitable for light to moderate loads and eliminates indefinite postponement, and C-scan is over moderate and to heavy loads. Very small variance in service time. Okay, if you have a light load, you use first come first serve. Moderate loads, you use the shorter seek time first, or maybe you can use scan or C-scan. Okay, then this is certainly a rotational ordering or rotational delay. So rotation is a search strategy that tries to optimize search time by ordering requests once the read-write head has been positioned. Okay, assume that the cylinder has 5 tracks. Each track contains 5 sectors. Okay, if you have a track here, let's say you have a track. So this is track. Okay, this is the tracks, and then each tracks have you have like five tracks. 1, 2, 3, 4, 5. Okay. Okay, let's say this is a track number 5. Sorry for my hand. So each track you have 5 sectors. So this is sector number 1, sector number 2. Maybe this sector number 3. This one is sector number 4. Or this one is a 5. But it started early 0, 1, 2, 3, and 4. So 0, 1, 2, 3, and 4. We have 5 sectors and we have 5 tracks. Requests are taken in the order they arrive. Each request is satisfied as it comes in. Let's see now the how this rotational ordering or rotational delay is calculated. So okay, first one, this is the parameters. Okay, this is the parameters. The head takes 5 milliseconds to move from one track to the next. So inter track, let's say track 0 to track 1, it takes about 5 milliseconds. Alright. And then initially position at track 0, sector 0, track 0, sector 0. Okay, track 0, sector 0. This is the starting point. It takes 5 milliseconds to rotate the cylinder from sector 0 to sector 4. From 0 to 4, from 0 to 4, takes about 5 milliseconds or 1 millisecond per sector. Okay, this is the rotational delay. This is the rotational delay. All right, 1 millisecond per sector, and then it takes about 1 millisecond to transfer from the sector, one sector from cylinder to the main memory. Okay, RAM. So this one will take about 1 millisecond. So you have here the seek time 5 millisecond, seek time plus the rotational delay and plus the data times transfer time, call it transfer time. So this is the transfer time, this is the seek time, and this is the rotational delay. When we say rotational delay, so it takes from, okay, let's say it start from track sector 00, track 0, sector 0, then I move to sector 1. So move from sector 1, the seek time is 0 because we did the same track, and then the rotational delay is 1 millisecond, and then the transfer time is 1 millisecond. So you solve this one, and then you have from then you move to track 1. So this is 5 millisecond because inter-track travel, a seek time. And then, okay, when the seek time, okay, let's say, okay, from the first one, 0 to 1, first it will travel from here to here, okay. So this, and but when it try to read the sector, the arm head will move the entire sector. So this process to this process, to this process is about 1 millisecond. Okay, this is the beginning. Okay, let's say from track 1. Okay, now it moves to track 1 to sector 4. It will start from the the end of the current sector and the beginning of next sector, and then we rotate 1 and 2. So you take about 2 millisecond. 2 millisecond. Of course, when on the sector 4, it will read the whole sector starting from the beginning to the end. So all this take about 2 millisecond. So you have 2 millisecond plus the 25 is 1 millisecond. Okay, now you start here. From track still the same track, so it's 0 millisecond seek time to sector 3. So you got 1, 2. Okay. Sorry. Okay. Track 4. So 1 and 2 and 3 at the beginning of the sector 3. But when the arm head is here, it will read the whole sector 3. Well, this take about 3 millisecond. 3 millisecond plus 1 millisecond. And then you move to sector 2. This is the sector 2. So seek time is 5 millisecond inter-track. And then you move from sector 3 to sector 0. So sector 3 to sector 0 will take 1 millisecond. This one is a 1 millisecond plus this one is 1 millisecond, and so on. You can do this. So this is 0.5. The search time, the seek time is easy, but the search time is quite a tricky because you must read the whole sector, and the beginning of each track, each beginning of each request, it will start at the end of that sector and the beginning of the next sector. So you have here search 1, 2, 3. We have search 1, 2, and 3. 1, 2, and 3 back to 1 here. So back to 1 here, and so on. So you take about 36 millisecond total time. The total time is the seek time plus the search time and plus the transfer time. So you have a 36 millisecond. So in previous one, the amount of time wasted due to the rotation delay can be reduced if requests are ordered within each track. So instead of previously you go let's say this track 1, track 2, and track 3. Okay, track 1, track 2, and track 3. So if it can be reduced if requests ordered within each track, so that the first sector requested on the second track is the next higher number. So this one, instead of serving 4 offers, it will serving sector number 3, sector number 4. So it is in order. The sector is in order, and of course, the track is in order, and the sector also in order, from the lower sector to the higher sector. So we reduce the time from 36 to 28 millisecond. So reduce significantly. So this is the search schedule of rotational delay. This means that it serves the lower order of the sector, mean within the same track and the lower order of the sector. So rate is what we call that. Rate actually redundant array of independent disks. A set of physical disks that drive that view as one logical unit by the OS. Okay, the idea of rate is, instead of using one large, one very large size disk, it's better to use the smaller independent smaller disk that act as a one big disk. It's more cheaper that way. Assume that several smaller capital disks are preferred because receiving data among several small disks, the system can simultaneously access request data from multiple drives. Instead of using one big drive, which is expensive and slow, you have a small capacity disk drive. Okay, so the system can simultaneously access the request data from multiple drives in a parallel way. So it will improve the input output performance and improve data recovery in case of a failure. So okay, this is the RAID. It's not a new technology, but still in use now. Like if you familiar with the network access storage (NAS), so you use a RAID system. Okay. Typical configuration may consist of 5 hard disks connected to a specialized controller. Okay, we have a 5 hard disks, 1, 2, 3, 4, 5. But the system will see like one big hard disk, one hard disk. So rate is, if you do it in this manner, is much more economical, more efficient way rather than to have one large size disk. So this is where the rate idea comes from. Software that coordinates data transfer from this resides in a controller. So you have like a controller here. Data is divided into segments called strips that are distributed across the disk in the array. A set of strips is called many strips. It's called a stripe. Many strips. The process is called stripping. The way that distributed across the disk in the array. So this is the sample. You have strip 1, strip 5, strip 2, strip 6, strip 3 and 7, and strip 4 and strip 8. Alright. So you have here strip 1, strip 2, large capacity disk. The software coordinates the transfer of data from the disk in the array to large capacity disk that is connected to the input-output system. The OS sees this config as one large capacity disk. Okay. The OS sees this config as one large capacity disk. So this is a RAID controller. So we have a strip 1, strip 2, strip 3 and strip 4, strip 5. And this is the configuration rate level. This is all for the, to provide better access and to provide some redundancy. Okay. Sector 0 is like no, rate level 0 is like no level of rate. Rate 1 is for mirroring or for some data backup, which is very expensive. And this one, Hamming code to correct, to detect and correct the error. So you have a word parity state, this all to detect a error and to provide a better efficiency for input-output system. So level 0 is no error correction, no redundancy. It's just like a normal system. Cannot recover from hardware failure. Suitable for transferring non-critical data. Rate level 1 uses stripping. Provide redundancy by having a duplicate set of all data in mirror arrays of this that has a backup in case of hardware failure. So a read request can be satisfied from the main array of the mirrored array. So can be satisfied from the main array or the mirror array. So whichever this you have one, you can request from the main array or the mirrored array. It's either one. Disadvantage is required twice as much effort because data must be written twice, but it provides a good redundancy and the most expensive. So level 2 use a very small strips, Hamming code for error detection and correction, and it is an expensive complex configure to implement. So rate level 2 also is also expensive. It is expensive because the number of disks in the array depends on the size of the strip. All drives must be highly synchronized in both rotational movement and arm positioning. Rate level 3 is modification of level 2 that needs only one disk for redundancy. Only one parity bit is computed for each strip, and it is stored in the designated redundant disk. Rate level 4 use the same strip scheme in level 0 and 1 but computes a parity for each strip, parity bit. Then store the parity in the designated parity disk for error checking. So advantage, if one drive fails, data can be restored using bits in the parity disk. We have a rate level 5 is like enhancement of rate level form. The parity strip is distributed across the disk to avoid the bottleneck created in level 4. So the parity strips is distributed across the disk. All the disks have that parity bit. And rate level 6 provide an extra degrees of error detection and correction because it requires two different parity calculations. Both parities are distributed on separate disks across the array and are stored in a strip that corresponds to that data strip. So it also provides redundancy because parities are distributed separate disks across the array and are stored in a strip that corresponds to that data strips. So one calculation is the same as the one used in level 4 and 5. The other is an independent data check algorithm.